let's try to solve this problem here. The figure above shows a graph of net force against displacement S for a 3 kg block. Okay, so this is not a usual force displacement graph. They specify that this F here is representing net force. So this is a net force against displacement graph. The net force is experienced by the block in the same direction as the motion along a flat horizontal surface. Okay, so if you want to think about the situation, there will be a flat horizontal surface and your block is probably on the surface, and the net force is being pushed. The net force is pushing the block in the same direction as the motion of the block along the surface. Okay, so let's say if the motion is to the right, then the net force will be pointing to the right as well. They're in the same direction as the motion along the flat horizontal surface. If its initial speed is 5 meters per second and s is equals to 0 meter, s is equals to 0. So it means by initially it is already moving with 5 meters per second, but you know that at the end it will not be 5 meters per second. Why is it not equal to 5 meters per second at the end of the journey? Because you know that there's net force. If there's net force, there will be acceleration. If there's acceleration, there will be change in velocity. So if there's change in velocity, it will no longer be 5 meters per second at the end of the journey. Okay, so now they say that determine the net work done on the block after being displaced through a distance of 8 meters. So after the journey of 8 meters, so let's write it down. After the journey for 8 meters, what will be the final velocity after that? What will be the final work done? What will be the net work done? When you see the word net work done, the net here has the same meaning as total work done. So you are finding a total work done of the block after 8 meters. But if you think about it, total work done is actually just the work done by net force. Okay, total work done is the same thing as the work done by the net force, and we know that the work done by the net force is actually equivalent to the area under the net force displacement graph. Okay, and you can refer back to the explanation video if you have any queries. But basically, the net force displacement graph, if you find the area under the graph, the area here will represent the work done by the net force, and work done by the net force is actually just the same thing as total work done. Okay, so if we know that, now what we need to do is just to find the area under the graph. Okay, so net work done, you can say W total or W net, that's fine as well. The net work done will be the area under the FS graph. Okay, so you can see that there's two big chunks of area in between 0 and 8 meters. The first big chunk will be this chunk over here. The second big chunk will be this chunk over here. Okay, so the first big chunk you can find it using, well, it's length times width again, or you can call it height times width. The height here is 2 Newton, and the width here it's 5 minus 1. So that's the first rectangle over here. Height is 2, the width is 5 minus 1. So this is your first rectangle. The second rectangle, the height is 1. You're going to minus it because it's on the negative side of it's in the negative region. And if your force is in the negative region, if your force is negative, that means by the force has already flipped direction. So now the net force is in the opposite direction to the direction of displacement. Previously, if the motion is to the right, then the net force is to the right. That's what happened during these first 5 seconds. But from the 5th second to the 7th second, what happened is the net force is in the opposite direction to the direction of motion. Okay, that's why the force is negative in value. Okay, so we just calculate this area as an absolute value. Then what we do is just minus it out. Okay, so the height over here is just 1. and the width over here will be 7 minus 5. Okay, so if you calculate it, you get 8 over here, you get 2 over here. So that means by the net work done will be 6 joule. Okay, so the net work done is 6 joule. Next, for question B, find the final speed of the block after being displaced through a distance of 8 meters. You know that the net work done or the total work done will be related to the change in kinetic energy. That's work energy theorem. And you know that the work energy theorem can be related to the final speed because you know that the kinetic energy is just half mv squared. So v is the speed that you're looking for. So you can open it up to become half mv squared minus u squared. So the net work done, just be net work done, okay. So now I believe you can substitute already. So net work done is 6. Half the mass will be 3 kg block. The final speed, you know that initially it starts with 5 meters per second. So everything can be substituted except v. So v will be generated if you put everything into the calculator. So I believe if you calculate it, you get an answer of 5.39 meters per second. Okay, so this question B here can only be done because what you're finding in A here is the total work done. If what you're finding in A is the work done by one single force, but not the net force, it's work done by an individual force, then you cannot use this work done to equate it with change in kinetic energy. Change in kinetic energy can only be equated to the total work done or the net work done. And the net work done is the work done by the net force, and because this is a net force displacement graph, therefore what you find in the area under the graph here is the total work done. Only you can use it in question B to find the final speed of the block. Okay, if this is work done by gravity or if this is work done by friction, let's say, then you cannot equate it with the change of kinetic energy because that is not the total work done. You have to prove that it's total work done, only you can equate it with the change in kinetic energy. So that's all for this question. Thank you very much.